Hello, welcome to the Toronto Geometry Colloquium. This is a weekly web series all about geometry processing.
And this colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. And every week, we'll have an opener talking about their cutting-edge research for 10 minutes, followed by the headliner giving us a keynote presentation.
Thanks for tuning in yet again to another episode. I'm especially excited for both of our speakers today. Both of them deal in very related topics and what could broadly be lumped into inverse graphics. Our opening speaker is zooming in cross-continentally from EPFL in Switzerland, where he's a PhD student at the Realistic Graphics Lab. You might have seen some of his work. You might have seen his work already on Twitter maybe, or on the viral YouTube channel 2-Minute Papers, and it'll be presented again at SIGGRAPH Asia in a few weeks. But if you missed all of these, or if you're going to miss it, don't worry, because he'll be talking about it very shortly, very soon. It deals with a very popular line of work called it's called geometry reconstruction, where you basically try to reconstruct a shape from a series of images. And this is very popular, and it's been a very long-standing challenge for graphics researchers and vision researchers alike. And oh my God, when you see the results from this paper, they're simply mind-blowing, and I'm sure that they're going to have far-reaching implications for the future of this problem or related problems. I hope you'll delight in the results like I did. Please welcome Baptiste Nicolet.
Hi, everyone. So let me share my screen. Otman, can you see? Is my screen live?
Yep, I can see it.
Great. Hi, everyone. I'm Baptiste, and I'm very excited to present our latest work on differentiable rendering with Alex Jacobson and Wenzel Jakob, called Large Steps in Inverse Rendering of Geometry. Let me start by briefly introducing differentiable rendering. The forward rendering process, which takes as input a description of a 3D scene and outputs a set of images, is now a fairly well understood problem. But the inverse problem that tries to infer certain parameters from images is extremely challenging. Estimating the inverse of the rendering function is usually intractable, so instead we aim to estimate its derivatives with respect to scene parameters. And this allows us to run gradient-based optimizations. Starting from a 3D scene, we render it with a differentiable renderer, and then compute an error based on a reference rendering. We then use automatic differentiation to backpropagate the derivative of this error to the input parameters. We can then take a gradient step to update the scene and iterate until convergence. Now, in this presentation, we'll focus on using differentiable rendering to optimize shapes. There are many ways to represent them, for example, using implicit or volumetric representations, but today we'll focus on triangle meshes, since it's probably the most common representation. Now, it's worth noting that computing gradients with regards to triangle meshes is a challenging problem on its own, but we sidestep it here. And instead, we aim to design a robust optimization procedure. Now, when optimizing geometry with a differentiable renderer, one would start with a set of renderings of the target shape, as well as a mesh to optimize. For example, here, a highly tessellated sphere. When doing that, one could expect obtaining results like this. However, simply plugging in a differentiable renderer is more likely to produce results like this, where we visualize the self-intersections in red. And by the way, when we stop the optimization here, only 15 of the thousands of faces in the mesh are not intersecting other faces. One really needs to look at the interior of the shape to see the extent of the damage. The resulting shape contains thousands of intersections. Most of the vertex budget is lost on the inside of the mesh, and that makes this model completely unusable. So why does this happen? To understand, we first need to look at the origin of the gradients when differentiating with regards to triangle meshes. Gradients come from two terms. The first is related to the vertex normals. Changing the orientation of each face will have an influence on how light is reflected from the surface, and that will influence the pixel color. This type of gradient is defined on all pixels containing the optimized shape. However, they have a small contribution and only encode local changes. On the other hand, pixels containing part of the silhouette of the shape will have an influence over how the silhouette evolves. And even a small perturbation of the silhouette can drastically change what is visible inside a pixel. Therefore, these gradients have a large scale, but they're very sparse as they are only defined on a silhouette. And that's especially true when using few viewpoints or when the shape is highly tessellated. So we have only a few vertices that have a significant gradient. And on top of that, vertices have no way of talking to each other. So pulling one vertex out will not update its neighbors, as one may want. The consequence is what we've seen before. A common way to mitigate this is to add some kind of regularization to the objective. And the most commonly used one is Laplacian regularization. In the general case, we can write the Laplacian regularization laws as a quadratic form defined by a matrix, which is usually a power of the Laplacian. In previous work with differentiable rendering, we have found that the bilaplacian was most commonly used. So we use this as our baseline. So with that in mind, we can come back to our optimization example and try to optimize a new objective that is now a compromise between a true objective and a regularization term. This requires carefully controlling the regularization weights during the optimization in order to converge to the right solution. And this is what we can obtain with this objective. As you can see, the result is quite a bit smoother than the naive baseline. However, it still displays many self-intersections, and a large portion of the mesh is still trapped inside the shape. This behavior is particularly visible when restricting our optimizations to a short window of time, which requires taking large gradient steps. So why is that exactly? To understand, we need to look closer at how the regularization behaves. So let's take a very simple example where we have a regular grid on a plane and only one vertex at the center receives a gradient. Since the shape is perfectly smooth at the start of the optimization, no gradients come from regularization in the first iteration. Then, as the center vertex is displaced, the regularization term will be non-zero for this vertex and its neighbors, and so will the gradient. So you can see that at each iteration, the smoothness constraint gets propagated only one edge at a time. Why is this problematic? Well, imagine now that our plane is highly tessellated. Then that means that it would take hundreds of iterations until the regularization affects the whole shape. And the problem is, during that time, the image objective keeps being optimized. And that makes it hard for the regularizer to keep up with the optimization. Now, the root of the problem here is that we're relying on first-order optimization, where this term here propagates very slowly on top of adding compromise in the objective. Laplacian regularization closely couples variables together, but first-order methods perform component-wise descent, which lacks this coupling. On the other hand, second-order methods account for this coupling by introducing the inverse of the Hessian. So it would be preferable to use this to update our shape. Now, unfortunately, this requires computing the Hessian of the rendering function, which is extremely large and dense, so it cannot be computed efficiently. Therefore, we approximate it by using the identity matrix. And since the inverse Hessian already closely couples vertex positions together, we can get rid of the regularization term in the gradients. And so this is the final form that we use for our method. Note that it is similar to the solution of heat diffusion on a surface, where in this case, the heat source is the original gradient. Note also that the approximated inverse of the Hessian is raised to a power p, which can be interpreted as taking p diffusion steps. Now, in practice, we use a value of 2 as it produces better results and enables a nice interpretation. There are actually several ways to interpret our method. As we have just seen, one can think of this update rule as an approximation of Newton's method. We can also interpret it as a form of Sobolev preconditioning. Sobolev preconditioning has been used over the years to solve various problems in geometry processing and in other fields. And note that we have not invented this, and we're merely pointing out its importance in differentiable rendering. But perhaps more importantly, our method can be thought of as a first-order method over a parametrization of the vertex coordinates. And this parametrization has a very familiar shape. By applying the Laplacian to the vertex coordinates, we can define a quantity called differential coordinates that encode the difference between each vertex and the barycenter of its neighbors. These have been widely used in geometry processing, mainly for intuitive editing purposes. Well, we propose a very similar parametrization, where instead of applying the Laplacian, we apply the Laplacian times a constant plus the identity. And we show in the paper that this indeed results in the same update rule as we've seen before. And this also provides a very intuitive interpretation for a hyperparameter. The closer it is to 0, then the closer we are to optimizing regular Cartesian coordinates, and the larger it is, then the closer we are to optimizing differential coordinates. And this parametrization is also extremely easy to implement and makes integrating our method into existing systems straightforward. All right, so let's look at some results now. Under the same setting as before, this is what we can achieve. This approach offers several advantages. First, it removes the compromise from the objective, thus avoiding the need to balance between two terms. But more importantly, it diffuses the gradients on the whole shape at each iteration, so we don't have issues with keeping up with the objective. Finally, as the matrix is sparse and positive definite, we can factorize and store it efficiently. As a consequence, the overhead introduced at each iteration by our method is small relative to the forward and backward rendering passes, which makes our method tractable. And this allows us to obtain satisfying results on a variety of target shapes, starting from very simple initial states. We can push this even further by combining our method with remeshing. To do so, we only need to recompute the mesh Laplacian and the factorization after each remeshing step. Since the time that this operation takes is on the order of a few optimization steps, this is affordable. And this allows us to recover complex shapes with multiscale optimization, like here, where we optimize this dragon starting from a simple icosahedron. So let's wrap up. In this talk, we have seen that using Laplacian regularization leads to unintuitive behavior and slow convergence that make it extremely brittle to use on challenging optimizations. By approximating a second-order step, our method enables a natural behavior that converges in fewer steps and is more robust. The icing on the cake here is that it's fairly easy to implement and integrate into existing systems, and the overhead it introduces is also relatively small. Now, finally, this method can also be applied to other domains where suitable Laplacian can be defined, although we leave evaluating its true benefits on these domains to future work. Thank you for your attention.
Thank you, Baptiste, for that beautiful presentation. Please post any questions anybody may have in the YouTube chat, and we'll get to them at the end in a joint Q&A session. Now, our next speaker is coming from the not-so-far cross-provincial McGill University from Montreal, where he's an associate professor in electrical and computer engineering. He's built up a large body of work spanning many different aspects of computer graphics, like fluid simulation control, rendering, and what he'll talk about with us today, differentiable physics. But I will admit, his research is only one aspect of why I'm so excited that he could join us today. The other being that he's one of the most passionate, dedicated, and engaging professors working in CS and engineering today. And I know this from firsthand experience, you see. He taught me my first graphics course during my undergrad around 3 years ago. And here I am still loving it today. It's not just my word. He was definitely a student favorite. Please welcome Professor Derek Nowrouzezahrai.
All right, thank you for that wonderful introduction, and thank you all for having me. Let me share my screen and hit play, and then we're off. Okay, great. Well, listen, I'm really thrilled to be here. Today I will be talking about differentiable physics, following quite in line with Baptiste's fantastic talk. Before I dive in, just want to quickly acknowledge that some of my slide content is either directly drawn from or inspired by two of my fantastic collaborators, Wenzel Jakob from EPFL and Krishna Murphy from Mila and Université de Montréal. And I'm Derek Nowrouzezahrai. As Ottman mentioned, I'm a faculty member at McGill University in Montreal. I'm also a core faculty member at the Mila. And here I direct the McGill Graphics Lab and the larger Center for Intelligent Machines. So today's talk, Differentiable Physics, Computer Graphics as an Inductive Bias, is, from the name, quite obviously talking about the combination of two fields that are near and dear to my heart. So the first is computer graphics, and the second is deep learning. And when I'm talking about the combination of these fields, much of sort of the meta aspect of my talk is going to be, what do I mean exactly by combination? And I'll see that there's several different ways that the two fields can come together. And at a higher level, I think I'm advocating for us to really cross-pollinate more between the fields. And I'm happy to see this happening most recently the last couple of years. So some examples of how CG and deep learning come together will be covered in my talk before I sort of double down on the direction that I'm most excited about in these combinations. So one of the ways that these two fields have come together are applications of deep learning to problems in graphics. So I'll be talking about some of the problems of graphics, and you can just think about deep learning methods as powerful data-driven tools for solving those problems. That's a very valid way of applying deep learning to computer graphics. Another way is how graphics-based techniques can be used to improve the performance of deep learning-based models. And I'll show you that the most prominent way that they're being used right now is as effective generators of high quality and high volume data. Okay? But this talk is really more about bridging this gap. And so when I talk about computer graphics and deep learning, really, I want you to think about, the size and distance between these arrows getting smaller and smaller, and maybe even the and becoming smaller and smaller. And it'll become a little more clear later on in the talk exactly what I'm talking about here. So before I do that, I'm actually gonna give a high-level overview of computer graphics in a nutshell. And this is purposefully oversimplified, and I'm gonna be missing a lot of important subfields. But at a very high level, you could think of computer graphics as being subdivided into three main subfields. The first of which is geometry representation and processing, where we think about how are the different ways that we can represent 3D objects that live in the real world. Okay, and here we see an example of polygonal mesh. And sometimes the choices that we make in how we represent these objects will impact what kind of operations we can perform on them. For example, can we deform them according to physics simulations? That leads us quite nicely into the second sub area of computer graphics, animation or physics-based animation, where we talk about how these 3D shapes evolve over time. And in doing so, we have to talk about the laws of physics, the laws of motion, and how we can be applying them to these 3D representations and evolving them over time. And then finally, the third subfield is rendering or realistic image synthesis. And as the name is viewed here, it's taking these evolving 3D structures and objects over time, and then generating a potentially realistic image of them. And the way we do that is we place a virtual camera in this virtual scene with evolving 3D objects. We place virtual light sources, and we attribute material properties to these objects. Are they made out of plastic or metal or wood? And then we run a second physics simulation, this time simulating the physics of light's interaction in the scene. Now, I've worked in each one of these areas and my focus has been in rendering, but today I'm actually going to shift a little bit away from rendering and focus more on the physics-based simulation part, okay? At this stage, it's kind of useful to abstract away these different components of the graphics pipeline into what the inputs are, how are they processed, and what kind of outputs do we care about generating, generally speaking. Okay, and with input representations, of course, there's how are we representing our 3D objects? And as Baptiste mentioned earlier in his talk, one representation that's very useful is triangular meshes, okay? But there are other inputs to the graphics pipeline. So for example, for the physics-based simulation of animation, right? How to evolve objects in space and time, right? Some of the inputs are the external forces that are applied on the objects, the masses of the objects, maybe coefficients of frictions if they're going to be colliding with each other. If they're deformable objects, their elasticity properties. These are all inputs to the system of the graphics pipeline. In the second part of the physics-based simulation, where we're simulating light, right? So the rendering part, there are additional inputs that I outlined earlier. What are the reflectance properties of my object? Is it made out of wood? Is it made out of metal or plastic? And if it's plastic, is it orange plastic or red plastic? Right? Where are the light sources in my scene? They're clearly going to impact the final image that I render. Is there texture on the object? And where's my viewpoint? What kind of camera do I have? And then finally, the outputs are either a single image, right? Or a sequence of images to form an animation, right? So this talk is going to focus primarily on the animation part of the physics simulation. So whenever I say a physics-based simulation, you could think of it as the evolution through time, but you can equally think about it as the composition of the evolution of time, which has a physics simulation in it, as well as the simulation of light to generate the images. Okay. So this is a good point for me to sort of hammer down what my central thesis is. And it's this. In cases where you're using data-driven techniques, machine learning-based techniques, to infer something about properties of objects in the real world, I'm going to claim that having what's called differentiable physics in the loop of this process will benefit those machine learning-based tasks in the settings where having some kind of understanding reality is beneficial. Okay, and here's maybe a couple of concrete examples of what I'm talking about here. So imagine you're giving any one of these image sequences, videos as inputs. Right, so here we see a duck that's sort of rolling on the floor. We have a deformable beam. We have a cloth that's falling on the bottom right, and a rigid tube that's bouncing off the floor. From these input images, I would like to use a machine learning-based technique that captures maybe a lot of data and observes these images to infer some kind of properties about the inputs to the physical simulation. And I want to maybe infer something about what the shape of the rubber duck is, or how much it weighs, or what the coefficient of friction is between the rubber duck and the floor that it's hitting. Right? That's one example of a learning-based task where if you have an understanding of how reality works, how the physics works, you'll probably be able to answer those questions, like what is the mass of the rubber duck, much more effectively. Another interesting task or problem that will leverage a better understanding of reality is, let's say I give you this target image of a biped that I can control with external forces. And I say, I want you to be able to make this biped move and wiggle and deform until it reaches this target frame. But you need to design a controller for this, right? A controller that's going to be activating the joints of this deformable biped over time, right? I want you to learn that controller just from this single target image. Can you do that? Well, the answer is it depends. And I'll talk a little bit more about what it depends on. So I want to sort of overview the different data-driven strategies that you can use in machine learning to start to answer these types of questions. And the first is using a pretty standard methodology of supervised learning. Okay, and there's no question that modern machine learning-based techniques are just a powerful toolkit for solving really complex problems where you can learn relationships between inputs and outputs from data. And generally speaking, the more data you have, the better. Now, if I wanted to learn something about the dynamics of the real world, and I only have data, I'll probably need a lot of data. Meaning if I don't imbue my model with any sense of what the physics is, to learn the underlying rules of physics from scratch will require a lot of observations, right? And so what we're saying here is, if I'm not going to have a neural network model that has any notion of what physics is to start off with, it doesn't have any physics-oriented biases or inductive biases, then its sample efficiency will be low. It's going to need a lot of samples, a lot of training data to learn that behavior from scratch. And what's more is it may have difficulty generalizing to unobserved behaviors. So if you don't have a certain behavior in your training set, it's not necessarily the case that it will be able to hallucinate it after not seeing it, right? So you need a lot of labeled data, which, by the way, can be extremely time-consuming and so too costly capturing or generating. And you need to guard against this idea of memorizing the training set that you observed versus really forming an understanding of what led to that training data. Okay. That being said, there's been a lot of progress in applying this methodology to the types of problems that I've talked about. And here we see our first instance of where computer graphics has really been useful. And that's been in the context of machine learning, that is. And that's been in the ability of generating a lot of labeled data. We run these simulations, we know what the inputs are, and so we can label the outputs and feed that into a supervised training loop. Okay, so that's one place where computer graphics is already making a huge impact. Still though, I'd argue that we're leaving a lot on the table, right? Because if we're not imbuing our neural models with any physics-based priors, you're still plagued with the sample inefficiency and generalizations issues. You're just somewhat bridging the gap by facilitating the generation of a lot of training data. Another really interesting area where computer graphics has been used in the context of machine learning is this simulation to real world transfer, where let's say I want to train the behavior of a real world robot, which we see here in the bottom row of the images. And I want to train it to learn some kind of task. Here it's composing a bunch of gears. Well, real world robots are expensive. They can be dangerous, right? And they are limited in the speed that they can move, okay? And those last 2 points are kind of related. Whereas simulating a robot in a computer graphics world is relatively cheaper. And I could simulate millions of robots on dozens of computers at a rate much faster than they can move in the real world. And so that's an area where I can use physics-based simulation composed of animation and rendering to generate a lot of training data that I can use to then train a neural network to learn the task that I want in the simulation world. And then once I have that trained in the simulation world, I can transfer that on fewer samples with real robots. Okay, now that's another really interesting use case. And there's a lot of really cool questions that we're going to come back to briefly at the end of the talk in this context, which is, how good does my simulation have to be? How much does it have to match a reality to bridge that sim to real gap? I think that's a really interesting question. But the thing to notice on this slide is these two stages are still completely disassociated from each other, right? I'm generating a lot of training data with my simulator, I'm training something on it, and then I'm going to be transferring it to the real world. Okay, so there's no direct connection between the physics and the real world transfer. So I guess what I'm advocating for is a more holistic perspective, right? And in this sort of computer graphics as a data generator context that I just covered, the graphics simulators really play no role other than generating cheap, voluminous training data. And we're going to take baby steps to get to the point that I want to, but we'll take them very quickly. And the first is I'm going to show that if your neural network has some kind of structure that's, let's say, inspired by the process that we see in the computer graphics pipeline, and that already serves to help bridge this sample inefficiency and generalization problem. And that gets us to the point where we can start asking questions of, well, instead of mimicking the graphics simulation pipeline in a neural network, why don't I just put the actual simulation in the neural network? And how do I do that? So let's talk about this first step. And to do this, I need to sort of motivate the importance of neural architectural priors. Okay, so the type of neural network that I have might be better or worse suited to a certain problem. And I think that here convolutional neural networks, CNNs, are a really great example of an inductive bias that happens to be well suited to a subclass of problems. In this case, image-based tasks. We've seen that neural network CNNs have been extremely popular and effective at solving many image-based problems. And the reason here is the structure of image space convolutions across scales and with compositional nonlinearities happens to be a really good way of describing important features, both locally and globally, in image space. And those features can be then processed in order to solve a certain end-to-end task, whether it's identifying how many cats you have in your picture, or how many people there are in the picture, or what are the contours of different objects. Okay, so a CNN is, all other things being equal, better suited architectural prior than, say, a more general architecture. Now here the asterisks say, there's a lot of different architectures that can be applied to these kinds of problems, and exploring the sort of relative pros and cons is outside the scope of this talk, but there is, some variability there as well. And so basically the takeaway with CNNs is, if your input image exhibits structure in image space, as most real world images do at least, there's no immediate reason to not consider applying a CNN. Okay, so there's no reason to not immediately think, okay, a good baseline would be for me to use a neural architecture that is a CNN. And I hope to convince you that a similar statement will hold in the case of physics-based problems and differentiable simulators. So I want to give one of my favorite examples of what I'm calling a graphics-inspired neural architecture, okay? And the one I want to talk about is Hologen. And this is a fantastic architecture where they're trying to synthesize images of, say, real objects or faces that you could then rotate. And instead of just applying a vanilla convolutional neural network, what we see here is they start by describing features in a 3D volume and associating rotations with actual rotations of this feature volume before then projecting it into image space. This starts to sound a lot like having a 3D representation of a scene. and then performing rendering, which one part of it is to project it onto the image scene, onto the image plane. So this is what I mean by imbuing your model with some kind of graphics inspired structure. And it turns out that if you're careful about how you do this, you can effectively learn parts of the graphics pipeline. You can learn the 3D to 2D projection. You can even learn to disentangle to a certain extent geometry, which lives in 3D, and shading, which happens, or which is observed in image space. And this allows them to basically rotate objects in images, okay? At least in a more sample efficient and generalizable way than had they not had these 3D volumes. So physics-inspired architectures, right? They constrain the design space to physically meaningful solutions. And it shouldn't be surprising that, this outperforms a general architecture. And we've seen this before. If I have a data-driven technique and I want to learn some dynamical system, if I constrain the parameters that I want to learn to be exactly those of the dynamical system that I care about, or the family of dynamical systems I care about, well, then I can learn different types of systems much more effectively from observations. And again, this is unsurprising. And I like to think of it as amounting to basically a physics-tailored feature engineering, okay? And again, this is just another example of a specific type of architecture well-suited to the domain that you're applying it to, just like CNNs were. Right? So it begs the question, in the context of physics-based architectures, right? Why don't we fully constrain our model, our neural model, based on the models of physics that we know from other fields or that we've used in computer graphics, if those are well-suited to the problems we're trying to solve? This is where we get into sort of the core of my talk, which is differentiable rendering. Okay, sorry, differentiable simulation, force and habit. So to talk about what a differentiable simulator is, first we need to talk about simulation in graphics. So physics-based methods in graphics sort of target two contexts, as I mentioned earlier. There's physics-based dynamics or animation, where we're going to model and simulate the laws of motion. And we're answering questions of the form, how do objects move, interact, and deform over time? Right? And then we have physics-based image synthesis or rendering, right? And this is modeling and simulating the scattering and measurement of light. How does light behave during image formation on a sensor like a camera or my retina, right? And we're going to omit the details of number two, of the physics-based image synthesis or rendering in this talk. And we're very lucky that Baptiste already gave us a very nice sort of intro to that problem setting. So how do we design physics simulators and then move to designing what are called differentiable physics simulators? So I'm going to be covering a huge domain in 2 slides. So this is necessarily an oversimplification. But generally speaking, the evolution of a physical system can be fully determined by its time-dependent state and its forward dynamics. And by state, I can mean any set of parameters, but here are some examples. Let's say I have an object, a bunny, that's a deformable bunny. Well, its state might comprise, its tessellation, right? If I'm dealing with a 3D tessellated mesh, so maybe the positions of the vertices and the connectivity of the faces of the triangle mesh. And at any given point in time, t, right, the state might also comprise, say, the vertices, the velocities at these vertices, and other state parameters that I'm just clumping together and calling theta here. So it could be the mass, elasticity, and so on and so forth. Right? And then we have the forward dynamics. And the forward dynamics describe the evolution, the change in the state over time with a function. Okay, and different functions will model different types of dynamics. Given these 2 points, we can then evolve our object, its state, really, over time by time integrating the forward dynamics as such, right? So if I want to get the next step in time for my state, I take the current state, and then I just integrate its forward dynamics by the step size. Okay? And this allows us to simulate all kinds of different deformations, rigid dynamics. It's all sort of captured by this function d, the forward dynamics. So forward physics solvers are simulation methods that we use in graphics, for example, but we've drawn on from other fields like optimal control engineering and physics, computational physics. And here, generally speaking, we're going to be using discrete time stepping variants to solve this problem, okay? And again, an exhaustive survey is outside the scope of this talk, but I'm happy to field questions about it. So generally, we're going to assume that we have a very simple time stepping process here where we just keep on composing D and integrating it over time steps in order to evolve our state over time. Okay. And this is where we get to distinguish between the forward problem and the inverse problem, right? So forward simulators solve the forward problem. They evolve the state of the dynamics over time and update our view of the world at any given time, right? So I want to determine all of the states of this deforming bunny over time, starting from 0 to whenever I care. And what I'm going to be doing is I'm going to be running my physics-based simulation function here on the inputs, right? And the inputs are the 3D mesh, friction coefficients, mass, external forces, all these properties that we care to have on the forward problem, right? And we have those as inputs, right? And the output is our state trajectory in a 3D space, let's say. Now, inverse problems seek to determine those inputs that led to observed state trajectories. So now we're swapping our inputs and outputs. Instead of having inputs that are, properties of the 3D world and the mass and the elasticity and external forces, and then wanting to solve for how that evolves over time, what if we see how it evolves over time and we want to infer things about the mass, the 3D meshes, the elasticity, right? So that's what the inverse solver does, right? It takes your state that you've observed and then tries to solve for the inputs of the forward solver, right? So this is an ill-posed problem, right? Because there's many types of inputs that can lead to the same observed state, okay? And so to solve this ill-posed problem, one common way is to minimize an objective over, say, the high-dimensional parameter space that I'm optimizing for, right? So I'm going to have some loss, and here I'm calling it a loss in 3D, and this is really important. I'm going to elaborate on this, which is, I'm trying to minimize this loss, which is the difference between the states that I've observed, right? The states that I've observed versus the simulation with my current guess of what the inputs would be, right? And here it's important to note that the states that we're observing here live in 3D. We're talking about mesh positions. We're talking about masses in the real world. We're talking about coefficients of friction at different points on all the objects, okay? And of course, physics simulation is in the loop here, okay? It's in the loop. We need to run the simulation. Now, the problem with this supervision, this minimization problem is we require 3D observed states, okay? We need 3D supervision, right? And it's difficult to get this, whether you're capturing it from the real world or even simulating it, right? So capturing and observing 3D data to run this optimization is difficult, right? And what I'm going to propose here is a full end-to-end differentiable graphics pipeline, meaning that we're going to combine differentiable physics and differentiable rendering so that we can solve these types of inverse problems using only 2D supervision just from observed images. So what am I meaning here? Now I want a loss that's not in 3D, right? It's a loss, let's say here, over a sequence of images, which I'm sort of visualizing in this kind of swept image format here, right? So now I'm really minimizing, some simulated objective here, right? So here, this is the full graphics pipeline, physics-based animation and physics-based lighting that generates an image or a sequence of images from observed images, okay? And that's the objective that I'm going to minimize, and I'm going to solve for the input parameters, 3D object positions, masses, evolution over time, right? That's going to minimize this image objective, right? And the key here is, again, we're learning 3D scene parameters, but we're learning them only from 2D supervision, and we have the full graphic simulation in the loop. Okay, so this is what that minimization problem looks like. We want to solve for X's, right? We can run the full graphic simulation to generate a sequence of images or a single image, and then we're going to compute the difference with what we've observed, right? And so the key here is we have the full 3D physics simulation in the loop, which includes lighting, shading, deformation, animation, and the laws of motion. We compute a loss, and then we use that loss to update our guess on what the real world state is. Okay, so this is very, very compositional, and it has a lot of moving parts. So just really quickly, when I compute the image loss, right, I then need to use that image loss to update my guess on X, right? Which means I have my image loss here, but I need to know how changes in pixels impact changes in 3D state, right? And that's a matrix of partial derivatives. Okay, then I can apply that matrix vector product to update my state, and I'm going to run this kind of iteration, this optimization over and over. Again, I don't want to sound like a broken record, but here it's clear that we have a compositional function in the graphics pipeline where we have physics and we have lighting. And there's nothing stopping us from focusing on differentiable physics simulations and differentiable renderers, and then just composing their individual gradients using the chain rule. Okay, so you could sort of deal with both of these differentiable physics problems separately and then compose them together at the end. And that is exactly what we do, right? So you have differentiable rendering and differentiable physics, and you can compose them together. And again, I'm not going to get into the details of the differentiable rendering, but you can assume that we have a relatively good and flexible differentiable renderer. Okay. So how do we come up with those partial derivatives, right? We know how to do the forward process with simulation. That's 40 years of graphics. But how do I work backwards from the outputs to the inputs and determine these gradients, right? I need to be able to compute estimates of the sensitivity of physics simulation outputs to its inputs, right? And there are several strategies in many other fields that work on exactly this type of problem, right? From sensitivity analysis to optimization to computational statistics, and certainly in machine learning, right? And the two main workhorse techniques for solving this problem are forward mode and reverse mode differentiation. So I'm going to quickly overview these. Let's say I had a physics simulator and I have the code for it and the understanding of the mathematical models. Okay, forward mode differentiation computes the gradients that we care about by propagating small changes in the inputs to determine what the small changes in the outputs are. Right, so I'm going to tweak my 3D input in order to determine how, after pushing it through the simulation, it corresponds to a 3D output change. Right, so if this is an abstraction of our 3D input state, mesh vertices, mesh masses, coefficients of friction, external forces, some of those are going to be going into our animation module, some of those into our rendering module, right? And they sort of combine together to give us the observed states, our images, right? And if I propagate small changes through the inputs through each one of these, I can compose that matrix that I care about for computing my loss. And that's forward mode. And it's actually relatively straightforward to implement a basic model of this. And it boils down to augmenting all of your floating point and vector data types with dual approaches that sort of propagate and carry through these gradients, these tiny changes, right? These finite differences. So there are some considerations here, right? In the sense that we're caring about solving problems that have many potentially high-res image inputs, so many pixels, right? As well as millions of input parameters, right? The vertices of each one of those mesh objects, right, will have 3 parameters. There's masses, external forces, so millions of inputs, which means this matrix of the all pair gradients, partial derivatives, can become very, very big, very, very fast, and can immediately, blow any memory requirements that you have to respect. Reverse mode differentiation, on the other hand, works by modifying, by perturbing the outputs and propagating backwards through the program flow, right, through your dynamics to determine what the changes in your inputs are, right? So here, I'm going to be perturbing my outputs a little bit and working backwards to propagate through my gradient. And I can do this in a much more parallelized way. The downside of reverse mode is that I now not only need to track the forward program execution, right, the forward graphics pipeline, but I need to be able to differentiate backwards through it. And so that's a second type of simulation or pipeline that I need to work on, right? And in the context of graphics, full graphics simulations, we have a lot, high dimensional input space, right? So I might be trying to infer properties about this moving bunny, and I'm only doing that after also modeling the forward dynamics of a rendering problem, right? Which means if I look at the computation graphs for these types of simulations, they can be absolutely mind-bogglingly large. Okay, I might have just invented an adverb. And so I need to be able to model that inverse process as well, and that could be costly in memory and in complexity. So the question here is, what are our other options? Right? Forward mode, which is also called tangent mode, is not flexible in cases where I have many input parameters, whereas reverse mode requires that I store this computation graph and be able to compute piecewise gradients that I compose across it. So it also has memory limitations. So there is one other important technique that's come to light of late, and that's the idea of an adjoint method, right? And this is because every, for the most part, forward dynamical system has an associated backwards adjoint system. And adjoint systems model the sensitivity of outputs propagating, quote unquote, backwards in time to the inputs. So if I have some model of forward dynamics, which is what we're using to use the forward physics simulation, I can compute a model of backwards dynamics to allow me to sort of work backwards through the simulation. And this adjoint relates to the differentiable physics systems as follows. Like once we solve the adjoint modeling problem, we can come up with the gradients that we need for differentiable physics, right? And the idea here is we can similarly time step backwards through the adjoint dynamics in order to infer something about the initial states. Okay, so the short and sweet of it is there's been a lot of work in this area on applying and determining what adjoint models are and how to simulate them backwards in time. So this is what the big picture looks like, right? I want to solve for questions of the form, what was the mass of my object? Where were its positions over time? What external forces? And I have a differentiable physics engine. Now in the past, if I was here and I had observed states, I can solve a 3D supervision problem if I can observe these states in 3D, but that's difficult. What we're instead saying is, what if I add a differentiable renderer in the loop? So now I don't need direct 3D supervision, but instead I can supervise directly against 2D images or a 2D image or image sequence, right? So that starts to bridge this 3D supervision gap, right? So this is our overall system, right? Is now I also have a differentiable renderer, which takes as input camera, colors, lighting, and so on and so forth. But my loss is computed just in image space, right? And I can propagate all the way back to those 3D states that I care to solve about. And our initial system that we've released in this space is called GradSim. So GradSim is a physics solver, a long time in the making, and it supports 2D image supervision with differentiable rendering. And just to give you sort of a taste for the engineering behind this is we implement this using a 2-level pipeline. So we take physics simulations that are expressed in Python, and we can process them to automatically compute the adjoint simulations, and then optimize those to run on massively parallel heterogeneous compute using C++ and CUDA. And because of this, we can also run these in massive fashions across a lot of data samples, all in 2D, using, say, GPU clusters. Okay. Here are some results. So the first task is I want you to estimate something about the parameters that in your scene using only images that you've observed. The first type of physics that dynamics that we support are rigid bodies. So rigid bodies obey ballistic motion, except when they hit things, okay? Well, except when there's collisions. Now, collisions are very tricky to handle because they're an instantaneous effect, which means their gradients are ill-defined. So we actually provide a little, we regularize this problem by relaxing the collision with a linear hinge. And for those of you who are in physics-based animation, this corresponds to a quadratic penalty energy. And that allows us to take image sequences like this and infer things about the masses and where the collisions are happening over time and so on and so forth. So I'm going to be showing a lot of results of this form. So let me just quickly explain what I'm showing here. This is going to be the initial guess of our optimization. And this is going to be the ground truth that we observe. So we're observing these image sequences and we're trying to optimize to a certain result, okay? So if this is my random initial guess of what the dynamics are, and I observe this image, after a little bit of observation, we're able to update our properties about the scene in order to reproduce this behavior, which is indistinguishable from the ground truth that we've observed. Here's another example where we have complex geometry, and because complex geometry, tiny perturbations can lead to many different collisions down the road in time. This is especially tricky. So take a look at the end here where the rubber ducky ends after the simulation. Okay, so sort of on the left side of its face. If I observe something where it just tips right on the beak, after a little bit of optimization with GradSim, we're able to reproduce that behavior. We also support deformable solids. And these are very challenging because there's self-intersection, and in some cases you want to maintain volume and pressure balances. Okay, so again, here we rely on existing simulations, and we maybe adopt them to regularize problems that would cause local minima optimization problems during the use of GradSim. So in this case, we add a sort of hyperelasticity support, and this is going to allow us to also handle thin shells, which you'll see in a second will involve this cloth demo where I have a thin cloth that's falling over time. So here's a nice example where we have a deforming rod. So this is my initial deformation guess, just with random initialization. This is what I observe. It's a little more stiff, a little more rigid. And after our optimization with GradSim, we're able to reproduce this result. Here, I have an initial guess, right, of the properties of this cloth. And what's interesting in this example is I'm only giving a single image, not the image sequence to optimize for, right? So I want to match this image at some point in time. And what we see is that we're able to get pretty close to this using, again, just a few iterations of optimization. I want to talk about one more task that I think is really interesting here, which is robot controller design, where here robot is used as a term that's used very loosely, right? So if I have a learnable physics-based model of the real world, and I want to control objects in it, well, that's another learning-based task, right? So GradSim allows us to embed dynamic differentiable physics in larger neural architectures, okay? So here I want to learn a simple MLP, neural network, right, to activate forces on a deformable object. And I'm going to use GradSim in the loop to do this. So I have this target, one image that I would like this deformable gear to hit at some point. This is my initial guess. And this is after optimization. I could design a controller that will hit that frame, that target frame, only from a single image. Here's another one. We saw that deforming biped, right? And what's nice here is you can see what our initial guess for our controller and how we're activating the different joints here. At 0 iterations, it just kind of sits still. And as you run these iterations, you can almost feel people rooting for the biped to make it to the end of the screen. So after 1 iteration, it doesn't quite make it. But then, after 2 iterations, we are able to hit our target. Okay, so that's very, very sample efficient. So what are some takeaways here? So for one, I hope I've convinced you that bringing these two fields closer together is a good idea, and that real world dynamics modeled by graphic simulations can drive a lot of really interesting future work in learning-based world exploration models. Okay, so differentiable graphics can significantly improve our ability to form this comprehensive model of the 3D world, because that's what we've been working on in graphics all these years, right? And GradSim is just our first iteration on trying to solve end-to-end tasks using this knowledge. And one really important problem among many that remains is bridging this reality gap. So all the examples I showed you were sort of cartoon-like, right? Compare this to that. And even that is not a fair comparison, because this isn't even really getting us close to anything that's that realistic, right? This object does not exist in the real world. So there's even a bigger gap to be reached here. So this is work that was conducted at Mila in the McGill Graphics Lab with my fantastic students. And none of this would have been possible without my collaborators and all their hard work as well. So thank you so much for your time. And I'm really happy to have been here today.
Thank you so much for that great presentation from Professor Derek Nowrouzezahrai. We're gonna let Derek take a quick break, or catch his breath, drink some water, and we're gonna go right for the Q&A session. So we have a few questions for Baptiste. So the first question we have is, does this optimization strategy that you use place any additional restrictions on the topology of the final mesh you come up with? For example, is it only limited to genus 1 meshes, genus 0 meshes?
Not particularly. So in the examples that we showed in the paper and in this presentation, we have mostly genus 0 meshes. We have one example where we optimize this Brouille mesh from a torus, so that's a genus 1 mesh. Also, this t-shirt. I mean, this t-shirt starts with actually the holes in the right, pretty much in the right place. So it's not, it has some holes punched in it so that, you could actually get the right topology. Otherwise, it would be much trickier. So it's a little bit more difficult to see because, it has the shape of a sphere. So it's not obvious, but the holes are already in place. So there are no real restrictions on the topology. I mean, it's just we just don't change it at any point. And then, as long as you can compute a suitable Laplacian, then you should be fine. One thing that could be done though is that when remeshing, you could use some fancier remeshing algorithm that actually enables changing the topology. We don't do that in our experiments. We just use some simple remeshing algorithm that was, by the way, implemented by Sylvia. Thank you, Sylvia. And so we don't change the topology. And actually, if you look at the cranium model that we have in the paper, you can see that there are some portions of the mesh that join but don't quite merge because you can't. And if you were to use something more fancy like LTOPO, then you would be able to merge those. So yeah.
Thank you very much. Yeah. Oh, just one more question though. What sort of bias is introduced when you replace that difficult to compute Hessian term with an identity matrix? Does it cause something to be too smooth that shouldn't be too smooth? I was just wondering if you had any intuition onto what that approach.
Right. So that's a very good question. So I don't really know what it would look like if you had the full Hessian, because it's, as I said, it's very difficult to compute. So but the thing is, we're not really interested in this Hessian term, because what we're really interested in is this inverse Laplacian that does what we want. So as I said in the talk, we remove from the gradient this regularization term. So in terms of the objective, we're optimizing only the true objective. However, the way we're, as you said, we're biasing the gradients pretty much. And this inverse Laplacian preconditioning, what it does is it's really dampening the high frequencies of the gradient, and it's amplifying the low frequencies. And so that's why you see this behavior in the videos where you sort of see it, the whole shape move around, and then the high frequencies start to move in. So the shape is not going to be too smooth if you wait long enough. It's just that the very fine details, the very high frequencies, they're going to be dampened quite a lot. So you might have to wait quite a bit longer than usual if you want to retrieve those very high frequencies. So maybe at some point you would want to either lower this hyperparameter or even disable the method altogether if you're already pretty close to your solution.
I see. Thank you very much. We have a few questions for Derek now. So in your talk, you talked a little bit about forward mode differentiation and reverse mode differentiation, but then you go on to talk about how you guys use the adjoint method, or an adjoint-based method. What sort of advantages are obtained from using such an adjoint-based method that aren't available to you using forward mode or reverse mode differentiation?
Right. So there's clearly a trade-off here. Okay. So some of the advantages are that you don't have to manage or store a computation graph and then have the overhead of computing, piecewise gradients, and that can involve quite a bit of engineering and tailored solutions. And also, you don't need to store explicitly this massive matrix. Okay? Those are some advantages. So they boil down to computational complexity and also memory requirements. Now, the trade-off here is that you still need to formulate the adjoint simulation model, and you need to simulate it, right? Which will, there's many ways of doing that. So the design space is in a certain way larger, right? So there's variability in those choices, and it doesn't come for free. That's extra work you need to do. You now are not just interested in running a forward simulation, but you have a separate simulation that you need to run backwards, right? And it has different sensitivity issues, different accuracy issues, and it doesn't work like magic, but it's just another tool in this arsenal.
Mm-hmm. And you mentioned the importance of involving a physical prior or a physical architecture in your neural network or in your optimization strategy, is there a principled way to evaluate the usefulness of this prior? For example, would a differentiable elasticity simulator be useful at all for maybe some sort of fracture or fluid simulation?
Yeah, that's a great question. Let me just unpack it a little bit. Is there a principled way to do this? I'm not sure. And that would be a fantastic way because whenever you're developing a suite of new techniques, you want to be able to answer questions with the form, how good is it? When does it break? And I'm not sufficiently knowledge. I don't have enough knowledge in this subdomain to really comment about all the other fields that look at similar problems and whether they have a principled way. If I had to venture a guess, I'd say in specific contexts, there are probably much more principled ways to benchmark against potential solutions in a very fixed problem setting. But I think the real challenge here, and that's what's so exciting about it, because there's a lot of really interesting work to be done, is that we are talking about a full end-to-end differentiable graphics pipeline. And I could tell you that in that setting, there's certainly no principled way of evaluating how to design a system and where the trade-offs are. I think there's a lot of work to be done there.
Yeah, very, very insightful and interesting future line of work, maybe. I have maybe a discussion question that maybe both of you could share your opinion on. We talk a lot about first order methods in deep learning physics, in physics simulation using deep learning methods. But Baptiste here shows that second order methods achieve amazing results when you know just the right way to use them. Is second order optimization a tractable way to learn physical neural network weights? Is that just something that's only very specific to Baptiste's problem, or what's the main limitation to using second order updates for traditional deep learning pipelines?
Baptiste, do you want to go first and then?
Okay, yeah. I think this work of ours is an interesting step in this direction. But as I said, this only aims at computing the Hessian term for something that we know extremely well. And for such a large system like a rendering system or a physics system, then it's much more complicated. So I guess with if you use automatic differentiation, then what you're computing is Jacobian vector products, and that we know how to compute pretty well. If I'm not mistaken, you can also use this to compute the Hessian, but what you want is not only the Hessian of your system, it's inverse, and this we don't really know how to do properly with automatic differentiation. So either you find an analytic solution or it's pretty difficult, I would say.
It's specifically inverting this large Hessian matrix.
I think so, yes. But maybe Derek has more to say about this.
I mean, I really like Baptiste's answer, right? Is that it's to be able to make effective use of a second order optimization technique, you need to solve a lot of big problems, which is determining the Hessian and to what degree of accuracy, and then actually really inverting it or approximating its inverse as in quasi-Newton techniques. And I think here the question of whether it's interesting to explore that line of work, I mean, I think the answer is yes, but I get easily interested in things. But I do also think that doing so, you have to take care of sort of the historical background of, there's a reason why SGS, stochastic gradient descent and first order techniques have been so widely adopted. They're not the only techniques that are being used. And of course, there's a lot of progress in second order techniques. But for large scale deep learning problems, SGD and SGD variants are the workhorse. And so if you want to look at this in the context, it depends on what your evaluation metrics are, right? If I care about solving an inverse physics problem with as few input training samples as possible or observations as possible, and I'm willing to throw, say, computation cost per iteration to the wind, then I think that if you're able to compose an effective second order or quasi second order technique, you'll probably hit high on that metric. But if I care about wall clock time or I don't know, sensitivity to noise in my observations, then these are different evaluation metrics, and maybe you're better off using a more approximate technique more often than a more accurate technique less often. in equal time. Maybe, I don't know.
Maybe we'll have to find out soon, hopefully. I think that's all the time we have for this session. So I'd like to thank both of our speakers for joining us here today. We have another session coming up next week that's going to be a very special hybrid session where we will have both, where we will combine this Toronto Geometry Colloquium with a local sort of get-together between Eastern Canadian universities. So please tune in next week for Alexa Su and Josh Halanadi. Thank you for attending this talk.